Train an AI agent with reinforcement learning and it gets better. But how much better depends on something most recipes ignore: the size of the model. A 2026 paper from CUHK and Idea Research demystifies this. Across roughly 180 controlled runs on a travel planning sandbox, the optimal recipe flips with scale. Small models need a staircase of rewards, large models need a single dense signal. Get it backwards and you leave more than 20 points of success on the table. The testbed is Travel Planner. 6 local tools: search city, flights, distances, restaurants, attractions, accommodations, orchestrated to satisfy common sense rules and hard constraints. A trajectory succeeds only if both dimensions pass. Even Kimi K2.5 scores under 15%. The paper trains Quen 2.5, instruct at 1.5, 3, and 7 billion parameters with a 3-stage pipeline called STAR. Synthesize over 10,000 queries, rejection sample, 1,200 gold trajectories, then reinforcement learning. STAR varies 5 design axes, 1 factor at a time: reward shape, model scale, data composition, algorithm choice, environment stability. The reward spectrum runs from dense SUM, all submetrics summed, to semi-sparse MACRO, just the macro scores, to purely sparse SUCCSS, only the binary win. And a curriculum that stages dense to sparse across 5 epochs. Every run is controlled. 1 factor moves, the rest stay fixed. And here's the headline: reward design is scale dependent. At 1.5 billion, the curriculum reward wins, 34.9% success. Plain dense SUM is worst at 33.1, move to 7 billion and it inverts. Dense SUM wins 62.8. Curriculum is now slightly restrictive at 57. Scaling the model nearly doubles SUM success, 33 to 63. Capacity is the primary bottleneck, and the right reward unlocks it. The crossover is the whole story. Plot success against scale for the 2 rewards. Curriculum starts ahead at 1.5 billion, 34.9, and stays strong at 3 billion, 49.9. But SUM climbs faster, 33 to 47 to 63, and overtakes curriculum at 7 billion. Dense reward is too noisy for a small model to credit. Assign over long horizons, but a large model has the capacity to use every signal. No single reward is universally best. Picture the difference. A small model is a traveler crossing a stream on scattered stepping stones. It needs the curriculum to place each stone, dense reward early, sparse reward late, or it falls in. A large model is a traveler on a single paved road. It just needs 1 dense signal and it walks straight to the goal, same destination. Completely different path. That is the scale-aware recipe. And data difficulty matters as much as reward. Easy-only data learns common sense but fails hard constraints, 45% success. Hard only collapses to 26. Successful trajectories get too rare, the reward starves, and even common sense decays. Mixed data, a blend of easy, medium, and hard, resolves both, 50%. There is also a sweet spot on quantity. 1,000 prompts peaks at 35% out of distribution, while 2,000 overfits the training distribution and drops to 32. The same inversion shows up in algorithms. At 1.5 billion, exploration-heavy ARPO and DAPO beat plain GRPO, 37 versus 30. At 7 billion, GRPO wins, 62.8, and at the lowest cost, 368 GPU hours versus ARPO's 547. The practical shift. For strong base models, skip the fancy exploration. Stage your rewards for small models, simplify them for large ones. Mixed difficulty. Stop scaling data past the sweet spot. A scale-dependent recipe for long-horizon reinforcement learning agents. Stage rewards for small models, simplify them for large ones. Mix difficulty data at 1,000 prompts, not 2,000. Plain GRPO once the model is strong enough. Open weight 1.5 to 7 billion models beating proprietary 100 billion to trillion parameter LLMs on Travel Planner. The paper is Demystifying Reinforcement Learning for Long-Horizon Tool, using agents, code linked below. The honest scope, 1 testbed, models up to 7 billion. But the core finding travels. The best recipe is a function of scale. Subscribe for the next breakdown.